What's up, guys? And today we are back to another chapter on system design fundamentals, and we're going to discuss about coordination and consensus. There are five friends, and one question is, where do we eat tonight? Everyone has an opinion. Everyone's typing once. Somebody suggests pizza, somebody else biryani, two people vote different things, and one friend's phone is on silent, so they're not even replying. Now, how does that group actually decide? One final answer that everyone agrees on is even though the people are talking over each other and one person is unreachable. That messy little problem is one of the hardest problem in computer science. When many computers have to agree on one thing, who's in charge, what the correct value is, and what order things are happened in, it's called coordination and consensus. And getting it right is what keeps distributed system from descending into chaos. So let's dig in. Now, you'd think agreeing is easy. It's brutally hard for the three reasons. They're the same reasons your friend group struggles. The first one is messages get lost or delayed. You text biryani and just don't arrive or arrives late. Computer face this constantly. The network drops and the delays message all the time. Then two is the participants can disappear. A friend's phone dies mid-conversation. A computer can crash at any moment, maybe right after it agreed to something, but before it told anyone. The three is no shared clock. We just learned this last lesson. Nobody has a perfectly synced sense of time. So, who spoke first is genuinely unclear. Put those together and you get the core challenge. How do a bunch of unreliable computers over an unreliable network all end up agreeing on the exact same answer? Now, that's consensus. Computers can't just vibe it out like friends do. They need a strict, provable method. Now, here's the first big idea, and it's one of your friend group uses instinctively. Pick one person to decide. Instead of five people arguing, the group says, okay, Aisha, you choose and we'll go with it. Now, there's one clear decision maker. No more chaos. In distributed system, this is called leader election. The computer picks one machine to the leader that makes decisions and everyone else follows. Now, why does this help so much? Because coordinating one decision maker with many followers is way easier than getting everyone to argue it at every time. The leader decides, tell the others, and done. But you saw it coming. What if the leader crashes? What if Aisha's phone dies? Then the group needs to notice she's gone and elect a new leader fast and without two people both thinking they are the leader at once. Detect the leader is dead, pick a new one safely. Dance is exactly what real systems like databases and coordination service do behind the scene constantly. So, how does the group agree who the leader is or agree on any single value when the people are unreliable? The answer is beautifully democratic, the majority vote. Now, here's the key insight you don't need everyone to agree, you just need more than half. If there are five computers and three of them agree on something, now that's the majority. And here's the magic. Any other majority must share at least one member with the first one. So two conflicting decisions can never both win a majority. That overlap is what makes the whole thing safe. Now this is the heart of famous algorithms you'll hear about. That is paxos and raft. You don't need the details right now. Just hold the intuition. Decisions are made by majority agreement. So the system keeps working even if the minority of the machines crashes or goes silent. Five machines, right? So you can lose two and still function because three are still in majority. Now that's not just clever, that's how systems survive in real failures. One friendly warning. This is why you'll often see clusters with an odd number of machines. 3, 5, 7. An odd number makes more than half clean and avoids ties. Little details, big consequences are there. Now here's an example. Real systems do this all day. Take a database that keeps 3 copies of your data for safety. Those 3 copies elect a leader. The leader takes all the rights and the other copies from it. Now, if the leader crashes, the remaining 2 hold a majority vote. Pick a new leader and the database keeps running. You, the user, never even notice that. Now, tools like Zookeeper, etcd exist purely to do this coordination job for the systems. They're the reliable group organizer that everyone else trusts to keep the agreement straight. Now, when you hear those names, think the friend who runs the board. Now, the one line is consensus means unreliable machines agreeing on one answer, usually by electing a leader or deciding by the majority vote. You don't need everyone, you need more than half. The majority overlap is what keeps two conflicting decisions from ever both winning. Now, it's why systems survive crashes. As a recap, agreement is hard because network drops messages, machine crashes, and clocks drift. Systems solve it by electing a new leader and making decisions by majority. So they keep working even when a majority fails. Next lesson, we hit one of the most famous ideas in all of system design, that is the cap theorem, which says that when the network splits, you have to choose between staying consistent and staying available. You literally can't have both. So see you there. Let's like and subscribe and catch you in the next one.